Okay, short little lecture here today, kind of finish out the last topic, which is steel columns. Okay, turns out you might be like, oh my god, look at all this stuff that's happening. It turns out the design of these things aren't too bad, okay, because you have design aids, because AISC is no dummy. So, um, let's do this. Okay, just real quick review. All right, limit states, yielding. For these are columns. Here we got yielding, global buckling, and local buckling. Local buckling is not going to be an issue, so it's going to be one of these cases: yielding or global buckling. Okay, and buckling would be like over the height of the column. We briefly talked about what buckling, the buckling phenomenon, and what causes it. It's basically if this P times delta is bigger than the moment, the restoring force that's there that puts it back into place, then the thing collapses. Okay. We talked about, well, you solve this differential equation and you get this for your critical buckling load. That's specifically for a pin-pin connection. What if you don't have a pin-pin connection? It's going to change your capacity. That's what this effective length factor is all about. You're looking to adjust that P critical based off of that effective length factor, that K there. We talked about what shows up in AISC. This is what shows up in AISC. We have this limit state and this limit state. This actually accounts for two limit states. This is yielding and inelastic buckling, and this is elastic buckling. And notice that it is straight up Euler buckling with this 0.887 or 0.877 out front. That 0.877 is to account for initial crookedness. Okay, so how would you use this thing for design, or how would you design these things? Well, right, what you're trying to look at, typically what you're going to have for a demand is an axial load, a support conditions, and overall length, right? And so you could theoretically look at this, use these equations and kind of back solve for the required R that you would need, radius of gyration that you would need in order to make this thing work, okay? Or in order to design something, and then you can have some table based off of ours. But AIC has got a better way of doing it. They've got these load tables, right? These things we have fabricated structural elements. They all have, they know what all of the dimensions are. They know what the materials are. Since they know all this stuff, why not just put all these capacities in a table, okay? And then order them in such a way that you can design these things and come up with the most efficient design. And they've done this, okay? But we'll get to that in a second. One last thing to talk about. So we're getting into the design. So we got a couple things. What kind of columns are there out there? Okay, that's the next topic, is types of columns. We've got types of columns. We have circular columns. Oh, I wanted to make a perfect circle. Circles. Or they've got these guys too, squares. And what these things are, we've seen these before, but these are, right, the circles can be pipes. Okay. The other thing, circles can be HSS sections, and same thing with the square columns or the rectangular columns that are also HSS. Okay, those things are hollow structural sections. The other thing I know, I keep calling these things columns, but really, even when they're talking about column design, right? I mean, obviously column types and different types of columns. Really, these are all compression members. Any kind of compression member has the capacity like this, okay? That's calculated according to this methodology. And you have to worry about buckling, and you have to worry about buckling, and you have to worry about yielding. Those kind of control any kind of compression member. And chapter E might even. What is chapter E? Let's see here. Yeah, see, chapter E is just design of members for compression. It doesn't necessarily call them columns. Okay, any compression member, primary compression member, would be covered by this whole section that we're talking about. But and so the reason I guess that I came up with that is, or why I want to talk about it right now. These are very common. You find HSS and pipes used specifically for columns, right? You see those things all the time. These guys you would not see as columns. Angles, okay, double angles. I could draw a better double angle than that. Okay, double angles, T-beams. move this guy a little bit down. T-beams. You won't see those things as columns, but you will see them as compression members. But in particular, you're going to see these things in trusses. And trusses are very common, okay? And you're going to see those. You're not going to see a column made out of a T and a double angled stuff like that, but you are going to see truss elements, and in particular, compression truss elements, and those things will be controlled by what we're talking about, okay? In this particular case, these things get a little bit more complicated because, we'll get back to that in a second, okay? And then the other members you're going to see are I-beams, okay? I-shaped members, okay? These things get used as columns, okay? And in particular, W12s and W14s are most common. Okay? If you're going to design a column out of a wide flange, you're probably going to use a W12 or W14. Why? I don't know. That's just the standard. It might have to do with like fitting in walls and framing and stuff like that. It might have something to do with that. I should ask a real engineer why that is. Okay, but then those are the columns. Where things get in all of these things, we'll just say design. This kind of could fit in the next section as well. Complicated by Rx not equal to Ry. Complicated, again, related to this, strong versus weak axis. Okay. The reason I kind of had it here, or why I've historically talked about it here, is because these guys, wide flanges, your Rx does not equal your Ry. Same thing with these components right here. Rx is not equal to Ry, meaning that there is a strong axis and there is a weak axis. If you're doing a design where you have a strong and weak axis, it gets more complicated, okay? Because you could have different span lengths for the different directions, okay? In these particular cases, right, obviously your Rx, you're going to have a strong and weak axis in bending, right? And same thing with these guys, you're going to have a strong and weak axis in bending. Harder to bend it around this axis, right? Easier to bend it about this axis, okay? And so if you think about it, if you apply a load to this guy, right, it's more likely to buckle about this axis, right? Because that's not the strong direction. It'd be a moment kind of acting this direction. It's going to be easier to do it because your area isn't spread out as much. About this axis, it's going to be a bigger issue, or it's going to be less of an issue rather, because, right, it's your strong axis, so it's not going to buckle that way, okay? And so this is just a little introduction. These types of members where you don't have Rx equal to Ry, it gets a little more complicated. These Rx is equal to Ry when you use square columns and you use a circle. Rx is equal to Ry, and so the design ends up being a little bit easier, okay? So to expand on that idea of having a strong axis and a weak axis, okay, that's what this drawing over here is for, okay? So I've got a load applied to this, right? A big axial load like this applied to this member. Well, you can see that these are supposed to be these are the flanges on the wide flange. So my strong axis is going left and right, okay? And then my weak axis is coming into and out of the board, right? So I apply a load on this thing, immediately you're going to be like, well, if I just took, I mentioned last night, if I just had a yardstick and I applied a load on the yardstick, it's gonna buckle on the weak axis, right? It's gonna pop out on towards the weak axis. It won't buckle over the strong axis because it's stronger that way. It's not going to go that direction unless I support that weak axis. If I support the weak axis up the height of this thing at multiple locations, I can apply a load. Yardstick maybe is a little extreme because it's so much stronger in one direction, but you can imagine something that's off balance a little bit. If I support it in the middle a little bit, I can cause it to fail over the strong axis, right? If I support it in the weak axis enough, I can cause it to buckle over the strong axis instead, okay? And so that's what I'm trying to show here. A lot of times we don't know what is going to control. So in this particular case, right, this beam right here is going to apply. This is going to apply weak axis support, right? So it's a beam coming, from above the board, and it's coming in, and it's bearing into the side of this wide flange section, and it's going to prevent the middle part of this thing buckling out. Okay, and so we're going to be comparing, whereas in the strong axis, this beam will do nothing to prevent it buckling this direction. Okay, and so in the strong axis, it's going to have a higher L, right? And then in the weak axis, it's going to be a smaller L, but it's also weaker because it's the weak axis. We don't know what is going to control. Is it going to be buckling around the strong axis over a larger distance, or buckling over the weak axis over a shorter distance? Okay, we don't know, right? It has less resistance to buckling there because it has a smaller Ry. Okay, and then here has a bigger resistance to buckling because it has a bigger Rx, but it also has a bigger L. So it's unclear. So you have to end up checking both of those things. That's kind of leading us up to a topic above. And so just to kind of finish the thought here, right? This right here, in this particular case, the way I have this thing drawn, this is going to be, I often go like this, I call it KL over R in the X. Okay? Because really, you can have you can have an effective length factor. What did happen to my X? You can have effective length factor that's specific to a direction. You can have a length specific to a direction. You can have an R specific direction. So just putting it outside of that parentheses, just saying all of these things are with respect to X. In this particular, for this example right here, this is what my KL over R would be this distance right there, because I'm not supporting this thing in the strong. If I had another beam coming in like this, okay, if I had another beam coming in like this and supporting this thing, sure, then my unsupported length would be that height right there. But in this case, there is nothing in the strong axis. And so this thing, if this were to buckle about the strong axis, would buckle out like that. Okay. Now, in terms of the Y direction, that's this. This would be KL over R. Okay. And then I'm going to call it Y1, right? The way I have it drawn right here, they're going to be the same, but there could be a case where it would be different. You could have different KL. Right? I could have a different KL over R for this lower span versus here, right? If this thing was off center, if my support was there, right? If my support was there, then I'd have one KL here, and then I'd have another KL there. If I had a fixed condition at the top and a pin down at the bottom, I could end up with a different K for each one of these spans as well. Okay, and so there you go. I mean, this is hopefully you get the point there. I don't want to beat this horse to death. Okay, but I do notice that I do that when I'm recording these lectures. I do have a tendency to beat the horse to death, because it's like I'm not getting any feedback from it. It's like I'm not picking up I'm not picking up if you're picking up what I'm putting down. Okay, and so it's like I'm just gonna end up repeating myself a lot. So I do apologize. But the good news is with YouTube, just fast forward and stuff. So anyways, KL over R, KL over R, KL over R, right? It turns out what's going to control is the one that has the biggest KL over R value, right? Is it going to be the KL over R X? Is it going to be the KL over R Y1 or the KL over Y2? Right? That is what's going to control our design. If you look back at the equations, they are a function of KL over R, right? And that will govern in which direction it's going to buckle, is which one has the largest KL over R. I was going to say largest KL over R controls. Okay. So you get to this idea that complicates this design a little bit, is this idea of buckling over which axis. Okay. And so design aids. What do we use for the design aids? Okay. Well, again, AISC is no dummy. They've put together a beautiful design aid. This is table 4-1. Okay. And this is in the column tab. Okay, so you're going to want to look at, again, back to tabbing your steel manual, you're going to want to go through and find table 4.1 in your steel manual and put a little tab on it. Okay, and so you can find that thing. Okay, so this table 4-1, I guess let's take a quick look at it. We'll do that example in a second. So this is table 4-1, right? How is this thing structured? Okay, what it is, first off, they only make these tables for W12s and W14s. Right, that's their standard size that they're going to deal. Right, we mentioned before those are the standard wide flange sections that we're going to use. I think they use them for like, I think they have them for HSS and things like that. But in terms of wide flange sections, right, these wide flange sections, they just have this table for W12s and W14s. So on different pages, W14 as well. Okay, and so how is this structured? Well, these are W12s by 96s, by 87s, by 79s, by 72s, and 65. So each one of these things are all different members, right? This is W12 by 96, 87, right, and so on. So these are all different members, okay? So those things are structured right there. And then we have phi-pn for each one of those members, okay? And then what varies as we go down here is the KL, okay? The effective length factor. So if you had something that had a KL of 14 feet, you would read up this 14 feet and you read across this thing until you find the phi-pn that's going to work for you. Okay, is how you work this table. Okay, but right, it's not too complicated, right? It's a little bit different than the ones we're used to working, but it's not too bad, right? You come up, say you enter it with your demand of what your PU is. You got to find a phi-pn that's bigger than your PU. You know what your KL is, and then you find your KL in this table, and then you read across until it works. Okay. If it doesn't, you can't find it on this page. Then you go to one of the other pages, and then this table continues on for different sizes of members on the different pages. Okay. 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 Just looking for one thing. Okay. So the other thing to note is this is one of those things where AIC is very creative. Okay. These things, these tables, table 4-1, assumes that the bar or that the beam buckles about its weak axis. Okay. So this is, see this RY right here. It assumes that it's going to buckle about its weak axis, which is going to be most likely going to happen if you just had no supports or on the, I mean, it is what's going to happen if you have no intermittent supports on your element. Okay. So one way that they could handle this, right? What if it's going to buckle about its strong axis? Like we said before, like, right, it's this whole problem, right? Is it going to buckle about its a longer distance around its strong axis or a weaker axis around a shorter distance? Okay, we don't know. So one way they could have done this is they could have made tables like this that had Rx instead. Right? That these tables were based off of KL over Rx instead of KL over Ry. But then that steel manual they have would be even thicker. Okay? And so what they've done is they've come up with a method so that you could still use this table, but use it with the Rx values instead. You can use this weak axis buckling table to help you design for the strong axis. Okay? And that's what we're going to cover next is how do we go about doing this. So table 4-1 in the column tab. So this thing, just kind of finish off or to kind of formalize that thought. These are assumes weak axis buckling, right, which is y-axis. Okay. Right. But then we're going to use these things for x-axis buckling. Use let me give it a little bit KL. Oh, I think I can type this KL Y equivalent. I spell it right. I did. Look at me, first try. Okay, KL Y equivalent. Okay, and we'll explain what that is in a second. Okay. And it's just a way of using that table for the strong axis. You use the same table, but you just come up with another way of like an equivalent KL for the strong axis. Okay, and how you do that is this: you say KL equivalent. KL Y equivalent is equal to our KL x divided by the quantity of Rx divided by Ry. Okay? And so what this does is Rx over Ry is going to be bigger than 1. Okay? Right? Because Rx is your strong axis and Y is your weak axis. So this number is always going to be, this is your radius gyration, your resistance, your section properties that resist buckling. So Rx is always going to be bigger than Ry. So this number is going to be bigger than 1. And then you take the strong axis and you divide by a number bigger than 1, and so it brings it down to a smaller number. Okay, and so it brings it down to like an equivalent weak axis unsupported length. Okay. What's an easy way to put this? I mean, that's it. That's the process, basically. Is you do that. Okay, and I got to think about the best way to explain this. It's equivalent. Let's see what it would do. For the same. This is convoluted. I'm going to type it out here. I'll give you the same load. I'm still here. I'm trying to think of the best way to explain how that works. If you can think of it in terms of the same load. I'm going to come back to that. I've done it mathematically before to try to explain what's happening there. Right. I mean, what you're ultimately doing, okay, is this is a bigger number, right? And you're dividing by a number greater than 1. So you're looking at a smaller number, okay? And so what you're really after, okay, is at what load will the thing buckle about its strong axis, okay? We're after what load will the thing buckle about its strong axis. It'd be great if you just had a table that was based off of the strong axis so you could look up that capacity, okay? But we don't have one of those things, okay? So what we do is we look at, we kind of reduced that unsupported length, right? This will have a higher capacity than something to be about its weak axis, right? It's going to have a higher capacity. And so what they do is they pretend that it's shorter. That's exactly what they do. That's maybe how we think about it. We pretend that the column is shorter, that it has less of an unsupported length than it actually does, so that we could calculate that reduced capacity. That's exactly what it is. Wrap your head around that a little bit. We pretend. Let me write that down. Let's see if that works. Oh. We pretend column is shorter than it actually is, which will increase its load. We pretend the column is shorter than it actually is, which will increase its capacity. I don't like that. This is what a cluster is. I'm going to come back to that one. I got to come up with a better explanation of this, okay? The idea, I get a brain fart here a little bit. All you need to know right now, okay? All you need to know right now is that we're taking this bigger number, we're pretending that it's shorter, right? So that when we look at the capacity, that's what it is. Because when we look at the capacity on the weak axis bending, right? It's gonna say it has a higher capacity for that load because we're trying to use a weak axis bending table to make it work. Okay, that's it. It's hard to put into words entirely. I need to spend some time with that one. Okay, But do understand this. We have to do this, right? What do you need to know in order to do these problems? We need to make this a KLY equivalent so that we can use the weak axis bending table. In that weak axis bending table, we pretend that this bigger length is shorter so that it will give us a higher capacity. Which would be equivalent to if we were to calculate the KL over R in just the X direction. Okay. Anyways, we need to do this. Okay. And then when you do this, and again, when we do an example, hopefully it'll make a little bit more sense. Okay. And then the largest KL Y or KL Y equivalent controls. Okay. Or like we mentioned before, or the largest, I mean, this is the same thing, KL over R controls. Okay. It's either one of those things. It ends up being the KL over Y versus KL over Y equivalent. It would give you the same results if you looked at KL over RX versus KL over RY. I need to come up with a better explanation of that. I think I could show it mathematically. I used to show it mathematically, and then I cut that out, and I was just like, you don't need to look at the mathematically of what's happening, but and for whatever reason, I have the biggest brain fart. I keep wanting to try to explain it again, and I can't do it right now. Okay. Okay. Anyways, losing my mind. This is where it'd be great if you guys were here, because then you could put it into. But I think you get it. And you probably go, "What the hell's this guy doing? What did he tell me?" Okay. Which is legit right now. Okay. Why doesn't he just say this? Okay. Anyways, we'll come back to this. So we're gonna do this. KL over Y equivalent, KL over X versus KL over Y. Those things control. So let's do an example. Okay, here's an example where we have weak axis is strong axis buckling. Okay, pretty simple example. We have a pin, right? Pin. Right here, we're applying a load like this. Okay, the strong axis is going into and out of the board. That's what this is trying to show. So like if you were to look down, that's what this is showing. If I was looking down on this thing, okay, it would look like this. Okay, it'd be the I-beam. So that means that the I-beam is kind of going into it. The strong axis is going into and out of the board here. Okay, and then at the weak axis, we've applied a support, right? And you could think of this as this could be maybe a beam coming in. And there'd be something that would be holding that weak axis, keeping the weak axis from buckling. Okay, and what we're asked to find, or what we're asked to do, is design the lightest weight W12 that works in this application. Okay, and so this is one of those cases where we have strong and weak axis. We got a longer strong axis, right? This only supports the y-axis, not the x-axis. And so we've got this overall height about the strong axis, and we've got this guy about the weak axis. Okay, and so what I always do, I always start these problems like this. Okay, and I think it's worth doing. This one's not too bad because it's pretty straightforward. But I always just to make sure everybody's on the same page here, as I draw these little axes right here, and I'll do one over here as well. Okay, and then I'll say that this is, we'll do the x-axis first, and this is the y-axis here. Right, buckling about either one of those axes. And what I like to do is I just kind of draw the deflected shape so you can capture what's happening. So a strong axis, okay, the strong axis is going to buckle over this height, right? There is no support in the strong axis. This support would move with it. It would not. Strong axis buckling is into and out of the board, so you can't really draw that on this figure over here. But if I were to draw it, if I kind of look at it from the side here, if I kind of looked it back on the side, its buckling shape would look like this. Oh, I'll just draw it. Need to be dashed. Okay, it's going to look like that. All right, because it's going to buckle over the entire height because there is no other supports in there. Oh my gosh. Okay, fair enough. And then around the weak axis, okay, there is a support right here in the middle. Okay, so let me draw that line over there just so you can see. Okay, there's a, well, it's supposed to be in the middle here. Okay, and so if we drew that deflected shape, okay, we have a pin on the top, a pin in the middle, and a pin down at the bottom. So it would do, God, that's not in the middle. I didn't make my lines big enough. So anyways, it would do this. Okay. It would buckle like that, right? And the idea behind it, right? It's a pin here, a pin here, and a pin here. Your homework problem is a little bit more complicated than that, right? It's not going to have just a pin, and a pin. It has, I think, 3 separate spans, and you got to play around with this a little bit. But when I start these problems, that's the first thing I do is kind of look at the deflected shape so I know what's happening at these different things, right? I know it's doing this because it's a, it's a pin, and so I know a pin, it goes like this, right? And then we got a pin from here to here, and so it would go like that, right? And if we look back at this table, what we're messing around with is these types, right? Here's a pin, here's the pin type of connection. But if I had like a fixed support at the bottom and a sway condition at the top, my deflected shape would look like this, okay? If I had a pin and a fix, my deflected shape would look like this. Okay, and then if it was a pin fixed pin, it would go back to the pin up there. Okay, I always like to start with that just so I can kind of piece together what's happening here. Okay, and so these are the two things. In this case, my K is equal to 1.0, and so my KL would be 26 feet. Right, so for a pin connection, K is equal to 1, and KL is 26 feet. In this case here, this is K again is equal to 1.0, right? Same thing down here. This is K is equal to 1.0, right? And KL in this particular case would be 13 feet. And this KL would be 13 feet, okay? And, right, for this particular case. If it was, well, we'll look, if it was, this is what I was trying to say earlier, if it was like a fix down at the top and then a pin, and then maybe a translation and a sway there, if the axial load like this, right, that deflected shape would be, it would be allowed to shift but not rotate. Allowed to shift but not rotate, and then it would come in like this. It would look something like that. Okay, just to give you an example, that's kind of why I do these little drawings, just so I understand, right? This guy is allowed to translate to the side but not rotate, but the pin doesn't stop anything with rotation, so it would just come in like that, and so it would sway out like this, but then this bottom support says that the rotation has to be 0 coming out, and so it would look like this. And so in this case, I would come in and I would say, well, yeah, K is equal to, in this case, 0.8, in this, the K is equal to 2.0, right? And so if this is all about the weak axis, then you'd have a KL for this span and a KL for this span as well. And there's nothing to say that these would have to be even spans. These could be different span lengths as well. This could be, 10 feet, and this could be 20 feet, right? And so by doing this little drawing right here, it's nice because you can come in and you can specify what your K is and your KL are, and just so you kind of know everything that you're dealing with. To me, it's way helpful to do that to begin with, okay? This is just an example, not to confuse. Okay, that's own little thing. I just don't want to make you to. I don't want you to confuse it with everything else that's happening. Okay, it has nothing to do with this exact problem. Okay. Anyways, you got the K's, you got the L's, you got the KLs, and so we can start this design. Okay. It gives us a PU of 900 kips. It's a lot of kips. 900,000 pounds. A lot of kips. But we're going to pick the lightest weight W12 to work right here. Okay, and this has already been factored because it's the PU is given to us. Okay, and so we enter these tables. Right? Pretty easy. You don't have to write much to do these problems. You say, well, PU is equal to 900 kips, okay? And my KLY, you have to start out with Y because I need an RX over RY. So we say KLY is equal to 13 feet, okay? And I can't do the KLX yet because I need to do the KLY equivalent. I got to come up with a KLY equivalent, but you have to start with the weak axis because I need to figure out what RX over RY is for the type of members we're dealing with. Okay, so what I do is I go to table 4-1 and I design for the weak axis first. So maybe line weak axis first. Okay, and so I come into this table 4-1, and I